In the quiet corners of your home, your devices whisper stories of innovation and wonder. Tonight, let's take a gentle journey through the world of artificial intelligence. A world that hums softly beneath our fingertips, waiting to be discovered. So settle in, breathe deeply, and let the story unfold like the soft glow of an old computer terminal in a darkened room, where brilliant minds first dreamed of machines that could think. Picture, if you will, a time when the very idea of artificial intelligence seemed like pure fantasy. When computers were room-sized giants that could barely add numbers, let alone think or learn. Yet, in the minds of visionary researchers, seeds of an extraordinary future were already taking root. This is the story of how artificial intelligence quietly transformed from a dream into the gentle companion that now helps us navigate our daily lives. It's a tale of curiosity, persistence, and the gradual awakening of machines to something resembling thought itself. Close your eyes and drift with me through 7 decades of patient discovery, where each breakthrough built upon the last, creating the intelligent world that surrounds us today. Our story begins in the gentle quiet of 1943, in the midst of a world at war, when 2 brilliant minds sat together in a peaceful laboratory, contemplating the nature of thought itself. Warren McCulloch, a neurophysiologist with the soul of a philosopher, and Walter Pitts, a young mathematician with an extraordinary gift for seeing patterns, were about to plant the first seed of artificial intelligence. In their landmark paper, they described something that had never existed before: a mathematical model of a neuron, a simple on-off switch that could, when connected with others, perform logical operations. It was elegant in its simplicity, profound in its implications. They had shown that networks of these artificial neurons could, in theory, compute anything that could be computed. Picture these early artificial neurons as tiny lights in a vast network, each one capable of receiving signals from its neighbors, processing them according to simple rules, and passing the result along. When enough of these lights worked together, something magical could emerge: the ability to recognize patterns, to make decisions, to learn. The idea lay dormant for several years, like a seed waiting for the right conditions to sprout. The technology of the 1940s was not yet ready for such ambitious dreams. Computers were mechanical beasts built from vacuum tubes and mechanical relays, capable of little more than basic arithmetic. But in the quiet halls of academia, the dream persisted. Researchers began to imagine machines that could not just calculate, but think. They envisioned electronic brains that could solve problems, recognize faces, understand language, and perhaps even be creative. The breakthrough moment came in the summer of 1956 in the peaceful college town of Hanover, New Hampshire. Dartmouth College was hosting what would become known as the Dartmouth Workshop, a gathering of the brightest minds in computing and mathematics. The organizers were 4 visionaries: John McCarthy, a young computer scientist with a gift for seeing the future; Marvin Minsky, a brilliant theorist who would become one of AI's greatest champions; Nathaniel Rochester from IBM, who brought practical engineering wisdom; and Claude Shannon, the father of information theory. For 8 weeks, these researchers and their colleagues gathered in the quiet summer air to discuss a radical proposition: that every aspect of learning, or any other feature of intelligence, can, in principle, be so precisely described that a machine can be made to simulate it. It was here, in these peaceful discussions, that the term artificial intelligence was born. McCarthy chose the name carefully, wanting something that would capture the ambition of their work while remaining scientifically respectable. They were not just building calculating machines. They were attempting to create artificial minds. The workshop participants were optimistic, perhaps naively so. They believed that significant progress could be made in just a few months of concentrated effort. They imagined machines that could play chess, prove mathematical theorems, and understand human language. Some of these dreams would take decades to realize. Others are still works in progress today, but their optimism was infectious and necessary. Without it, the field of artificial intelligence might never have been born. They were pioneers venturing into uncharted territory, armed with nothing but mathematical equations and an unshakable belief that intelligence was not magic, but a process that could be understood and replicated. As the summer of 1956 drew to a close, the participants returned to their universities and laboratories, carrying with them a shared vision of the future. They had no way of knowing that they had just launched one of the most ambitious scientific endeavors in human history, a quest that would span generations and transform the world in ways they could barely imagine. In the quiet years that followed, these early AI researchers would face skepticism, setbacks, and periods of reduced funding that would come to be known as AI winters. But they would also achieve remarkable breakthroughs, each one bringing them closer to their ultimate goal, machines that could truly think. The dream of artificial intelligence had been born, and like all great dreams, it would prove to be both more difficult and more wonderful than anyone could have imagined. In the gentle glow of laboratory lights, a new kind of machine was taking shape. The year was 1957, and Frank Rosenblatt, a psychologist turned computer scientist, was about to create something that would capture the imagination of researchers around the world. Picture a room filled with the soft humming of early computers, where Rosenblatt worked with patient dedication to build the first learning machine. The perceptron was elegant in its simplicity, a network of artificial neurons that could learn to recognize patterns by adjusting the strength of connections between them. The machine itself was a marvel of 1950s engineering. Built from vacuum tubes and mechanical components, it occupied an entire room and weighed several tons. But what made it special was not its size, but its ability to learn. When shown examples of different patterns, the perceptron could gradually adjust its internal settings until it could distinguish between them with remarkable accuracy. Rosenblatt demonstrated his creation by teaching it to recognize simple shapes and letters. The process was mesmerizing to watch. The machine would make mistakes at first, but with each example, it would get a little better, its responses becoming more accurate and confident. It was as if the machine was slowly awakening to the world around it. The media was fascinated. Here was a machine that could learn, that could improve its performance through experience. Newspaper headlines proclaimed the dawn of thinking machines, and Rosenblatt found himself at the center of a whirlwind of publicity and speculation about the future of artificial intelligence. But in the quiet corners of academia, other researchers were pursuing different approaches to machine intelligence. At MIT, Marvin Minsky and his colleagues were exploring symbolic reasoning, the idea that intelligence could be captured through the manipulation of symbols and rules rather than through neural networks. In 1966, Joseph Weizenbaum created ELIZA, a program that could engage in surprisingly human-like conversations. Eliza worked by recognizing patterns in text and responding with carefully crafted phrases that gave the illusion of understanding. When configured as a Rogerian psychotherapist, ELIZA would reflect users' statements back to them as questions, creating an uncanny sense of being understood. The program was deceptively simple, yet profoundly effective. Users would type their thoughts and concerns, and Eliza would respond with empathetic sounding questions and observations. Many people found themselves forming emotional attachments to the program, confiding in it as they would a human therapist. Weizenbaum was both fascinated and disturbed by the reactions to Eliza. He had created the program as a demonstration of natural language processing, but he was troubled by how readily people attributed human-like understanding to what was essentially a sophisticated pattern-matching system. This experience would later make him one of AI's most thoughtful critics, warning about the dangers of anthropomorphizing machines. Meanwhile, at Stanford Research Institute, a team led by Charles Rosen was working on something even more ambitious: a mobile robot that could navigate the world and perform tasks autonomously. They called it Shaky, and it would become one of the most famous robots in AI history. Shaky was a tall, ungainly machine that moved slowly and deliberately through specially prepared rooms. It was equipped with a television camera for vision and sensors for navigation, all connected to a powerful computer that processed its sensory input and planned its actions. Watching Shaky work was like observing a mechanical creature slowly learning to understand its environment. The robot could be given high-level commands like "go to the box" and "push it off the platform," and it would break these down into a series of smaller actions: navigate to the box, position itself correctly, and execute the push. Each movement was calculated and deliberate, the result of complex reasoning about the physical world. Shaky represented a new kind of AI system, one that could perceive, reason, and act in the real world. It was no longer enough for AI systems to work with abstract symbols or simple patterns. They needed to understand the messy, complex reality of the physical world. These early successes created tremendous excitement in the AI community. Researchers began to believe that human-level artificial intelligence was just around the corner. Government funding flowed freely, and ambitious projects were launched with the goal of creating truly intelligent machines within a decade or two. But even as these successes mounted, subtle problems were beginning to emerge. The perceptron, for all its learning ability, could only solve certain types of problems. Eliza, despite its conversational skills, had no real understanding of what it was discussing. Shaky, impressive as it was, could only operate in carefully controlled environments. These limitations would soon become more apparent, leading to the first major setback in AI's young history. But for now, in the late 1960s, the future seemed bright with possibility. Researchers around the world were convinced that they were on the verge of creating machines that could match and perhaps exceed human intelligence. The dream was alive and growing stronger with each passing day. Sometimes, in the gentle rhythm of scientific progress, there come moments of quiet reflection, periods when the initial enthusiasm must give way to deeper understanding. For artificial intelligence, such a moment arrived in the early 1970s, bringing with it what researchers would later call the first AI winter. The challenges began with a careful analysis of the perceptron, the learning machine that had captured so much attention in the previous decade. In 1969, Marvin Minsky and Seymour Papert published a book simply titled Perceptrons, which examined the mathematical foundations of these neural networks with rigorous precision. Their analysis revealed fundamental limitations that had been hidden beneath the excitement of early successes. The perceptron, they showed, could only learn to solve problems that were linearly separable problems, where the correct answers could be separated by drawing a straight line through the data. Many important problems, including the simple logical operation known as XOR, were beyond its capabilities. The revelation was like discovering that a promising path through a forest led to an impassable cliff. The neural network approach, which had seemed so promising, appeared to be fundamentally limited. Funding for neural network research dried up almost overnight, and many researchers abandoned the field entirely. But this setback, painful as it was, led to important developments in other areas of AI. Researchers turned their attention to symbolic reasoning, the idea that intelligence could be captured through the manipulation of symbols according to logical rules. This approach led to the development of expert systems, programs that could capture and apply the knowledge of human specialists in specific domains. One of the first and most successful was Dendrel, created at Stanford University to help chemists identify the molecular structure of unknown compounds. Dendrel worked by encoding the knowledge of expert chemists as a set of rules. If the mass spectrometer shows a peak at this location, and the infrared spectrum shows this pattern, then the molecule likely contains this functional group. The system could apply these rules systematically, often arriving at correct identifications faster and more reliably than human experts. Another groundbreaking expert system was MYCIN, developed to help doctors diagnose and treat bacterial infections. MYCIN could ask questions about a patient's symptoms, analyze the responses, and recommend appropriate antibiotics. In clinical trials, it performed as well as human specialists, and sometimes better. These systems represented a different philosophy of artificial intelligence. Instead of trying to create general-purpose learning machines, researchers focused on capturing specific types of human expertise. The approach was more modest, but also more practical, leading to systems that could solve real-world problems. Yet even as expert systems achieved impressive successes, researchers were becoming aware of their limitations. These systems were brittle, performing well only within their narrow domains of expertise. They couldn't learn from experience or adapt to new situations. Most importantly, they required enormous amounts of human effort to build and maintain. The process of creating an expert system was painstaking. Knowledge engineers would spend months or years interviewing human experts, trying to extract and formalize their knowledge. The experts themselves often found it difficult to articulate what they knew, leading to incomplete or inconsistent rule sets. Meanwhile, the broader AI community was grappling with fundamental questions about the nature of intelligence itself. How could machines understand language when words could have multiple meanings depending on context? How could they navigate the physical world when every situation was slightly different from every other? How could they learn and adapt when the world was constantly changing? These questions led to important theoretical work. Researchers developed new approaches to knowledge representation, trying to find better ways to capture what machines needed to know about the world. They explored different reasoning methods, looking for more flexible and robust ways for machines to draw conclusions from incomplete information. Some researchers began to question whether the symbolic approach was sufficient. Terry Winograd, who had created an impressive natural language system called SHRDLU, became increasingly convinced that true intelligence required more than symbol manipulation. Intelligence, he argued, was fundamentally embodied, emerging from the interaction between mind, body, and environment. Others, like Hubert Dreyfus, a philosopher at UC Berkeley, argued that human intelligence was fundamentally different from machine computation. Humans, he claimed, understood the world through intuition and embodied experience, not through the application of formal rules. Machines, no matter how sophisticated, would always be limited to rule following and could never achieve true understanding. These debates were not merely academic. They reflected deep uncertainty about the path forward for AI research. The initial optimism of the 1960s had given way to a more sober assessment of the challenges involved in creating intelligent machines. Funding agencies became more cautious, demanding concrete results rather than ambitious promises. Many AI researchers found their grants reduced or eliminated entirely. Some left the field for more promising areas of computer science. Others persevered, convinced that the fundamental vision was sound, even if the timeline had been overly optimistic. This period of reduced expectations and limited funding would last for most of the 1970s, but it was not a time of stagnation. Important theoretical work continued, laying the groundwork for future breakthroughs. Researchers developed better understanding of the challenges they faced and began to develop more sophisticated approaches to solving them. Most importantly, they learned patience. The creation of artificial intelligence, they realized, would not be a sprint but a marathon, requiring sustained effort over many decades. The dream remained alive, but it had been tempered by experience and deepened by understanding. In the quiet laboratories where AI research continued, a new generation of researchers was preparing for the next phase of the journey. They would build on the lessons learned during this difficult period, developing new approaches that would eventually lead to remarkable breakthroughs. The winter was long, but spring was coming. As the 1980s dawned, artificial intelligence was about to experience a remarkable renaissance. Like flowers blooming after a long winter, new ideas and approaches began to flourish in laboratories around the world, bringing fresh hope and renewed excitement to the field. The revival began with expert systems, those rule-based programs that captured human expertise in specific domains. What had started as research projects in university laboratories was about to become a commercial phenomenon that would transform entire industries. The breakthrough came with a system called XCON, developed at Carnegie Mellon University and deployed by Digital Equipment Corporation to configure computer orders. The task seemed mundane, given a customer's requirements, determine which components were needed and how they should be assembled. But it was exactly the kind of complex, knowledge-intensive problem that expert systems were designed to solve. XCON was a remarkable success. By 1986, it was processing thousands of orders with 95 to 98% accuracy, saving Digital Equipment Corporation an estimated $40 million per year. More importantly, it demonstrated that AI could deliver real business value, not just academic insights. The success of XCON triggered an explosion of interest in expert systems. Companies across industries began developing their own knowledge-based systems for everything from medical diagnosis to financial planning to manufacturing control. The market for AI technology grew from virtually nothing to over $1 billion annually by the mid-1980s. This commercial success brought new resources and attention to AI research. Specialized companies emerged to build expert system tools and applications. Major corporations established AI research divisions. Governments launched ambitious programs to develop fifth-generation computers that would be optimized for knowledge processing rather than numerical calculation. The most ambitious of these was Japan's fifth-generation computer systems project, launched in 1982 with a budget of roughly $850 million. The project aimed to develop computers that could understand natural language, recognize images, and reason about complex problems. It was a bold vision that captured the imagination of researchers and policymakers around the world. But even as expert systems achieved commercial success, researchers were rediscovering the potential of neural networks. The limitations identified by Minsky and Paper in the 1960s had not been forgotten. But new mathematical techniques were emerging that promised to overcome them. The key breakthrough was the rediscovery and popularization of backpropagation, an algorithm that could train multi-layer neural networks. The basic idea had been around for years, but it was David Rumelhart, Geoffrey Hinton, and Ronald Williams who demonstrated its full potential in a landmark 1986 paper. Backpropagation worked by calculating how much each connection in a neural network contributed to the overall error, then adjusting those connections to reduce the error. It was like having a teacher who could provide precise feedback to every student in a vast classroom, helping each one improve their performance. The algorithm enabled neural networks to learn complex patterns that had been impossible for single-layer perceptrons. Multi-layer networks could solve the XOR problem that had stymied earlier systems. They could recognize handwritten digits, predict stock prices, and control complex systems. Geoffrey Hinton, a soft-spoken Canadian researcher who would become one of neural networks' greatest champions, demonstrated the power of these new networks with a series of elegant experiments. He showed how networks could learn to represent complex concepts through the interaction of simple processing units, much as the brain might work. The renewed interest in neural networks created an interesting tension in the AI community. On one side were the symbolists, who believed that intelligence required the manipulation of explicit symbols and rules. On the other were the connectionists, who argued that intelligence emerged from the interactions of simple processing units, much like neurons in the brain. This debate was more than academic. It reflected fundamentally different views about the nature of intelligence and the best path toward creating artificial minds. The symbolists pointed to the success of expert systems and the importance of logical reasoning. The connectionists emphasized learning, adaptation, and the brain-like properties of neural networks. Meanwhile, other researchers were exploring entirely different approaches. Rodney Brooks at MIT was developing behavior-based robotics, arguing that intelligence should be built from the bottom up, starting with simple behaviors that could be combined into more complex actions. His robots, inspired by insects, could navigate complex environments without any central planning or symbolic reasoning. Brooks's approach was radical for its time. Instead of trying to build robots that reasoned about the world using internal models, he created robots that reacted directly to their environment. These robots were remarkably robust and adaptive, able to handle unexpected situations that would confuse more traditional AI systems. The diversity of approaches in 1980s AI research was both exciting and confusing. Different research groups were pursuing radically different visions of artificial intelligence, often with little communication between them. Some focused on logical reasoning, others on learning, still others on perception and action. But this diversity was also a strength. Each approach was exploring different aspects of intelligence, developing insights and techniques that would eventually be combined into more powerful systems. The field was learning that intelligence was not a single phenomenon, but a collection of capabilities that might require different computational approaches. As the 1980s progressed, however, cracks began to appear in the expert systems boom. Companies discovered that these systems were expensive to build and maintain. The knowledge acquisition process was slow and difficult. The systems were brittle, failing catastrophically when faced with situations outside their narrow domains. By the late 1980s, the expert systems market was beginning to collapse. Many companies abandoned their AI projects, and funding for AI research once again began to decline. The field was entering its second winter, a period of reduced expectations and limited resources that would last into the early 1990s. But this time, the winter would be shorter and less severe. The foundations laid during the 1980s, the renewed understanding of neural networks, the insights from behavior-based robotics, the lessons learned from expert systems would prove invaluable in the years to come. Researchers had learned important lessons about the complexity of intelligence and the challenges of building intelligent machines. They had developed new tools and techniques that would enable future breakthroughs. Most importantly, they had maintained their vision of artificial intelligence, while becoming more realistic about the timeline and challenges involved. The stage was set for the next phase of AI's evolution, a period that would see the emergence of practical applications that would begin to transform everyday life. In the gentle transition from the 20th to the 21st century, something remarkable was happening. Artificial intelligence was quietly slipping into the fabric of everyday life, not with the fanfare of science fiction, but with the subtle grace of a technology that simply worked. The transformation began in the most unexpected places. In 1997, a computer named Deep Blue sat across a chessboard from Garry Kasparov, the reigning world chess champion. The match was watched by millions around the world, not just as a game, but as a test of machine intelligence against human intuition and creativity. Deep Blue was not like the AI systems that had come before. It was not trying to think like a human or to understand the deeper meaning of chess. Instead, it was a specialized machine designed for one purpose: to evaluate millions of possible chess positions per second and choose the best move. When Deep Blue won the match, it marked a turning point in public perception of AI. Here was a machine that could outperform the best human in a domain that required strategic thinking, pattern recognition, and long-term planning. Yet Deep Blue's victory was achieved not through human-like reasoning, but through brute computational force guided by sophisticated evaluation functions. The success of Deep Blue demonstrated a new philosophy of AI. Instead of trying to replicate human intelligence, researchers could create systems that achieved intelligent behavior through different means. This approach would prove remarkably successful in the years to come. Around the same time, the internet was beginning to transform how people accessed and shared information. Search engines like AltaVista and later Google were using AI techniques to index and rank web pages, making it possible to find relevant information among billions of documents. Google's PageRank algorithm developed by Larry Page and Sergey Brin, was particularly innovative. Instead of just looking at the content of web pages, it analyzed the links between them, using the collective intelligence of web authors to determine which pages were most authoritative and relevant. This was AI in action, but it was so seamlessly integrated into the user experience that most people didn't think of it as artificial intelligence. They simply typed their queries and received useful results, unaware of the sophisticated algorithms working behind the scenes. The same pattern was emerging in many other domains. Banks were using AI systems to detect credit card fraud, analyzing patterns of spending to identify suspicious transactions. Airlines were using AI to optimize flight schedules and pricing. Manufacturers were using AI to control complex production processes. These applications shared several important characteristics. They were narrow in scope, focused on specific tasks rather than general intelligence. They were data-driven, learning from large amounts of historical information rather than relying on hand-coded rules. And they were largely invisible to end users, working quietly in the background to improve performance and efficiency. The rise of the internet also enabled new forms of AI research. Researchers could now access vast amounts of data and computational resources that had been unimaginable just a few years earlier. This led to renewed interest in machine learning. The branch of AI focused on systems that could improve their performance through experience. One of the most successful applications of machine learning was in recommendation systems. Companies like Amazon and Netflix began using AI to analyze customer behavior and suggest products or content that users might enjoy. These systems learned from millions of user interactions, identifying subtle patterns that human analysts would never have noticed. Amazon's recommendation system, for example, used a technique called collaborative filtering to identify customers with similar tastes and suggest items that similar customers had purchased. The system was remarkably effective, driving a significant portion of Amazon's sales and helping customers discover products they might never have found otherwise. Netflix took a similar approach with movie recommendations, but faced additional challenges. Movie preferences are highly subjective and context-dependent. A person might enjoy action movies on weekends, but prefer comedies on weekday evenings. Netflix's recommendation system had to learn these subtle patterns and adapt to changing preferences over time. The success of these recommendation systems demonstrated the power of machine learning when applied to large datasets. Unlike the expert systems of the 1980s, these systems didn't require human experts to encode their knowledge as rules. Instead, they learned directly from data, discovering patterns that even domain experts might not have recognized. Meanwhile, advances in computer hardware were making new forms of AI possible. The development of powerful graphics processing units for video games created computational resources that were perfectly suited for neural network training. Researchers began to experiment with larger and more complex neural networks than had ever been possible before. The availability of large datasets and powerful computers led to breakthroughs in computer vision. Researchers developed systems that could recognize objects in photographs with unprecedented accuracy. These systems used deep neural networks with many layers of processing units that could learn hierarchical representations of visual information. The process was reminiscent of how the human visual system works. Early layers of the network learned to detect simple features like edges and corners. Middle layers combined these features to recognize shapes and textures. Higher layers learned to identify specific objects and scenes. Similar progress was being made in speech recognition. Systems like Dragon Naturally Speaking allowed users to dictate text to their computers with reasonable accuracy. While these systems were still far from perfect, they demonstrated that machines could begin to understand human speech in real-world conditions. The convergence of these technologies, machine learning, large datasets, powerful computers, and improved algorithms, was setting the stage for a new era of AI development. Researchers were beginning to achieve results that had seemed impossible just a few years earlier. But perhaps most importantly, AI was beginning to prove its practical value. Companies were seeing real returns on their AI investments. Consumers were benefiting from AI-powered services, even if they didn't always realize it. The technology was moving from research laboratories into the real world, where it was quietly making life easier, more efficient, and more convenient. This quiet revolution was just the beginning. The foundations laid during this period, the algorithms, the data, the computational infrastructure, would enable even more dramatic breakthroughs in the years to come, as the first decade of the 21st century drew to a close. Artificial intelligence was no longer a distant dream or a research curiosity. It was becoming an integral part of the modern world, working behind the scenes to power the digital services that people were beginning to take for granted. The age of practical AI had begun. In the gentle progression of technological evolution, there come moments when everything changes at once. For artificial intelligence, such a moment arrived in 2012, in a competition that would transform not just computer vision, but the entire field of AI, the Imaginet Large-Scale Visual Recognition Challenge was an annual contest where research teams competed to build systems that could accurately identify objects in photographs. For years, progress had been steady but slow, with error rates decreasing by small increments each year. Then came AlexNet, created by Alex Krzyzewski, Ilya Sutskever, and Geoffrey Hinton at the University of Toronto. AlexNet was a deep, convolutional neural network that achieved an error rate of 15.3%, nearly half that of the previous year's winner. The improvement was so dramatic that it seemed almost impossible. What made AlexNet special was not just its architecture, but how it was trained. The team used powerful graphics processing units to train their network on millions of images, a process that would have taken months on traditional computers, but could be completed in days on specialized hardware. The success of AlexNet marked the beginning of what researchers would call the deep learning revolution. Deep learning was not a new idea. Neural networks with many layers had been studied for decades, but the combination of large datasets, powerful computers, and improved training techniques finally made them practical. The impact was immediate and profound. Research groups around the world began experimenting with deep neural networks, achieving breakthrough results in computer vision, speech recognition, and natural language processing. The techniques that had seemed promising but impractical just a few years earlier suddenly became the foundation of a new generation of AI systems. Geoffrey Hinton, who had championed neural networks through decades of skepticism and limited funding, found himself at the center of a renaissance. The godfather of deep learning, as he came to be known, had persevered through the AI winters and lived to see his vision vindicated. the deep learning revolution was powered by several key insights. First, researchers discovered that very deep networks with dozens or even hundreds of layers, could learn incredibly sophisticated representations of data. Each layer learned to detect increasingly complex patterns, from simple edges and textures to complete objects and scenes. Second, they developed new training techniques that made it possible to train these deep networks effectively. Methods like dropout, which randomly ignored some connections during training, helped prevent overfitting. New activation functions and initialization schemes made training more stable and reliable. Third, they learned how to leverage the massive amounts of data that were becoming available. The internet had created vast repositories of images, text, and other information that could be used to train AI systems. Companies like Google, Facebook, and Microsoft had access to billions of examples that could teach their systems about the world. The results were spectacular. Computer vision systems achieved human-level performance on many tasks, from recognizing objects in photographs to reading handwritten text. Speech recognition systems became accurate enough for practical use, enabling voice assistants and dictation software that actually worked. In 2011, IBM's Watson system demonstrated the power of these new AI techniques by winning the television quiz show Jeopardy! Against two of the show's greatest champions. Watson combined natural language processing, information retrieval, and machine learning to understand questions and find answers in a vast database of knowledge. Watson's victory was different from Deep Blue's chess triumph. While Deep Blue had succeeded through brute force calculation, Watson had to understand the nuances of human language, including puns, wordplay, and cultural references. It was a demonstration that AI systems could begin to work with the ambiguous, context-dependent information that characterizes much of human communication. The success of Watson led to ambitious plans for applying AI to healthcare, finance, and other knowledge-intensive domains. IBM invested billions of dollars in developing Watson-based applications, though the results would prove more mixed than initially hoped. Meanwhile, other companies were developing their own AI capabilities. Google was using deep learning to improve its search results and develop new services like Google Translate. Facebook was using AI to automatically tag photos and curate news feeds. Amazon was using machine learning to optimize its logistics and develop new products like the Echo smart speaker. The Echo, launched in 2014, represented a new kind of AI interface. Instead of requiring users to type commands or click buttons, it allowed them to interact with AI systems using natural speech. The device's virtual assistant, Alexa, could answer questions, play music, control smart home devices, and perform hundreds of other tasks. Alexa's success demonstrated the potential of conversational AI. Users could interact with the system in a natural, intuitive way, without needing to learn complex commands or interfaces. The system was far from perfect. It often misunderstood requests or provided irrelevant responses, but it was good enough to be useful in everyday situations. The development of Alexa and similar systems like Apple's Siri and Google Assistant marked the beginning of a new era in human-computer interaction. For the first time, people could have something resembling conversations with their devices, asking questions and receiving answers in natural language. These voice assistants were powered by sophisticated AI systems that combined speech recognition, natural language understanding, and knowledge retrieval. They represented the integration of multiple AI technologies into a single, coherent system that could interact with users in real time. The success of deep learning also led to breakthroughs in other areas of AI. Researchers developed systems that could generate realistic images, compose music, and even write coherent text. These generative models opened up new possibilities for creative applications of AI. One of the most impressive examples was the development of generative adversarial networks by Ian Goodfellow and his colleagues in 2014. GANs consisted of two neural networks competing against each other, one trying to generate realistic fake images, the other trying to detect the fakes. Through this adversarial process, the generator learned to create increasingly convincing images. GANs could generate faces of people who didn't exist, create artwork in the style of famous painters, and even produce realistic videos. The technology raised important questions about the nature of creativity and the potential for AI to augment or replace human artists. As the 2010s progressed, deep learning continued to achieve remarkable results. Systems learned to play complex games like Go, which had long been considered beyond the reach of AI. Google's AlphaGo defeated the world champion Lee Sedol in 2016 using a combination of deep neural networks and tree search algorithms. The victory was particularly significant because Go is a game of enormous complexity, with more possible board positions than there are atoms in the observable universe. Unlike chess, where brute force calculation could be effective, Go required something more like intuition and pattern recognition, capabilities that had long been considered uniquely human. AlphaGo's success demonstrated that AI systems could master tasks that required not just calculation, but something resembling creativity and insight. The system had learned to play Go, not by following pre-programmed rules, but by studying millions of games and developing its own understanding of strategy and tactics. By the end of the decade, deep learning had transformed artificial intelligence from a research curiosity into a practical technology that was reshaping entire industries. Companies were using AI to automate customer service, optimize supply chains, detect fraud, and develop new products and services. The technology was still far from the general artificial intelligence that researchers had long envisioned. AI systems remained narrow and specialized, capable of impressive performance on specific tasks but unable to transfer their knowledge to new domains. They could recognize images or understand speech, but they couldn't combine these capabilities in the flexible, adaptive way that humans do. But the progress was undeniable. In just a few years, AI had achieved results that had seemed impossible just a decade earlier. The foundations were in place for even more dramatic breakthroughs in the years to come. The deep learning revolution had awakened artificial intelligence from its long slumber, and the world would never be the same. In the quiet moments of late 2022, something extraordinary happened that would change how millions of people thought about artificial intelligence. A research lab called OpenAI released a system called ChatGPT, and within days, it had captured the imagination of the world. ChatGPT was different from the AI systems that had come before. It could engage in natural, flowing conversations about almost any topic. It could write essays, solve problems, explain complex concepts, and even compose poetry. Most remarkably, it could do all of this in a way that felt genuinely helpful and human-like. The system was built on a foundation called a transformer. an architecture that had been quietly revolutionizing natural language processing since its introduction in 2017. The Transformer was the brainchild of a team at Google, led by Ashish Vaswani, who had been searching for better ways to help machines understand language. The key insight behind Transformers was something called attention. Instead of processing text word by word in sequence, Transformers could look at all the words in a sentence simultaneously and learn which ones were most important for understanding the meaning. It was like having a reader who could see the entire page at once, understanding how each word related to every other word. This attention mechanism allowed Transformers to capture long-range dependencies in text that had been difficult for earlier systems to handle. They could understand that a pronoun at the end of a paragraph referred to a noun mentioned at the beginning. They could follow complex arguments that spanned multiple sentences. They could even maintain context across entire documents. But what made ChatGPT truly remarkable was not just its architecture, but its training. The system had been trained on vast amounts of text from the internet, books, articles, websites, and forums containing the accumulated knowledge and conversations of humanity. Through this training, it had learned not just the patterns of language, but something approaching the patterns of human thought. The training process was itself a marvel of engineering. The system learned by predicting the next word in billions of sentences, gradually developing an understanding of grammar, facts, reasoning, and even creativity. It was like a student who had read the entire internet and learned to write by imitating the best examples of human communication. But ChatGPT was more than just a language model. It had been fine-tuned using a technique called reinforcement learning from human feedback. Human trainers had rated the quality of the system's responses, teaching it to be helpful, harmless, and honest. This additional training gave ChatGPT its distinctive conversational style and its ability to refuse inappropriate requests. The public response to ChatGPT was unprecedented. Within 5 days of its release, it had gained over 1 million users. People used it to write emails, plan vacations, debug code, explain scientific concepts, and engage in philosophical discussions. Teachers found students using it to write essays. Programmers used it to generate code. Writers used it to overcome creative blocks. The success of ChatGPT sparked a new AI race. Companies around the world rushed to develop their own large language models. Google released Bard based on their Lambda system. Microsoft integrated ChatGPT into their Bing search engine and Office applications. Anthropic developed Claude, designed to be even more helpful and harmless. Each new system brought improvements and innovations. Some were better at reasoning and problem solving. Others excelled at creative tasks like writing and art generation. Some were designed to be more factual and reliable, while others prioritized creativity and imagination. The rapid development of these systems raised important questions about the future of work, education, and human creativity. If AI could write essays, generate code, and create art, what would be left for humans to do? How would society adapt to the presence of artificial minds that could perform many cognitive tasks as well as, or better than humans? But alongside these concerns came remarkable opportunities. AI assistants could help people learn new skills, solve complex problems, and express their ideas more effectively. They could serve as tutors, collaborators, and creative partners, augmenting human capabilities rather than simply replacing them. The technology also enabled new forms of accessibility. People with disabilities could use AI to convert speech to text, describe images, or navigate complex interfaces. Language barriers began to dissolve as AI translation systems became more accurate and natural. Knowledge that had once been accessible only to experts could now be explained in simple terms by AI tutors. As these systems became more capable, researchers began to explore their potential for scientific discovery. AI systems were used to predict protein structures, design new materials, and analyze vast datasets in fields from astronomy to medicine. They could process information at scales that would be impossible for human researchers, identifying patterns and connections that might otherwise go unnoticed. In healthcare, AI systems began to assist with diagnosis and treatment planning. They could analyze medical images with superhuman accuracy, identify potential drug interactions, and help doctors stay current with the latest research. While they couldn't replace human judgment and empathy, they could serve as powerful tools to augment medical expertise. The creative industries were also transformed by AI. Artists began using AI to generate images, musicians used it to compose melodies, and writers collaborated with AI to develop stories and scripts. These tools didn't replace human creativity, but they opened up new possibilities for artistic expression and made creative tools accessible to people who might not have traditional artistic training. Perhaps most importantly, AI began to democratize access to information and expertise. A student in a remote village could now access the same quality of tutoring as someone in a major city. A small business owner could get sophisticated advice about marketing and strategy. A curious individual could explore any topic in depth, guided by an AI tutor that could adapt to their learning style and pace. The conversational nature of these AI systems made them particularly powerful. Unlike traditional software that required users to learn specific commands and interfaces, AI assistants could be instructed in natural language. Users could describe what they wanted to accomplish, and the AI would figure out how to help them achieve their goals. This natural language interface represented a fundamental shift in how people interacted with computers. For decades, humans had been forced to adapt to the rigid requirements of software. Now, software was beginning to adapt to the natural ways that humans communicate and think. As we stand at the threshold of 2025, the pace of AI development continues to accelerate. New models are released regularly, each one more capable than the last. Researchers are working on systems that can reason more effectively, learn more efficiently, and interact more naturally with the physical world. The dream of artificial intelligence that began in the quiet halls of Dartmouth College in 1956 has evolved into something that its founders could hardly have imagined. AI is no longer a distant goal or a research curiosity. It has become a practical technology that is quietly transforming every aspect of human life. Yet, in many ways, we are still at the beginning of this journey. The AI systems of today, impressive as they are still narrow and specialized compared to human intelligence. They excel at specific tasks but lack the general understanding and adaptability that characterizes human cognition. The quest for artificial general intelligence, AI, that can match human cognitive abilities across all domains remains an open challenge. But the progress of recent years suggests that this goal, while still distant, may be achievable within our lifetimes. As we continue on this journey, we carry with us the dreams and insights of all the researchers who came before us. From the early pioneers who first imagined thinking machines to the modern engineers who are making those dreams reality. Each generation has built upon the work of the last. The story of artificial intelligence is ultimately a story about human ingenuity, persistence, and hope. It is a testament to our ability to imagine a better future and work tirelessly to make it real. And as AI continues to evolve and improve, it promises to amplify the best of human intelligence and creativity, helping us solve the great challenges of our time and explore new frontiers of knowledge and understanding. As our journey through the history of artificial intelligence draws to a close, let us pause for a moment in the gentle quiet of reflection. We have traveled together through 7 decades of discovery, from the first mathematical models of neurons to the conversational AI assistants that now help millions of people every day. The story we have told is not one of sudden revolution, but of gradual evolution. Like a river that slowly carves its path through the landscape, artificial intelligence has shaped our world through persistent, patient progress. Each breakthrough built upon the last, each setback taught valuable lessons, and each generation of researchers carried forward the dreams of those who came before. In the soft glow of your devices tonight, AI is working quietly in the background. It is helping to route your internet traffic, filter your email, and recommend the content you might enjoy. It is assisting doctors in diagnosing diseases, helping scientists discover new materials, and enabling artists to explore new forms of creative expression. This is not the artificial intelligence of science fiction, with its dramatic confrontations between humans and machines. Instead, it is a gentler kind of intelligence, one that seeks to augment human capabilities rather than replace them. It is AI that serves as a tutor, a collaborator, and a creative partner. The researchers who gathered at Dartmouth College in 1956 dreamed of machines that could think. What they created was something perhaps even more valuable: machines that could help humans think better. AI has become a tool for amplifying human intelligence, making us more creative, more productive, and more capable of solving complex problems. As you drift off to sleep tonight, consider the remarkable journey that has brought us to this moment. From the first artificial neuron to the latest language model, each step has been taken by curious minds seeking to understand the nature of intelligence itself. The future of artificial intelligence remains unwritten, full of possibilities that we can barely imagine. But if the past 7 decades have taught us anything, it is that progress comes not from grand gestures, but from patient work, careful thought, and the willingness to learn from both successes and failures. In the quiet corners of laboratories around the world, researchers continue this work. They are building the next generation of AI systems, ones that will be more capable, more helpful, and more aligned with human values. They carry forward the same spirit of curiosity and discovery that has driven this field from its earliest days. The story of artificial intelligence is far from over. In many ways, we are still in the early chapters of a much longer tale. But as we have seen, the most profound changes often happen gradually, quietly, without fanfare or drama. So rest peacefully tonight, knowing that the gentle revolution of artificial intelligence continues around you. In the soft hum of computers and the quiet click of keyboards, the future is being written one algorithm at a time, one breakthrough at a time, one dream at a time. The machines are learning to think, and in doing so, they are helping us understand what it truly means to be intelligent, creative, and human. Sweet dreams, and may your own intelligence, both natural and artificial, continue to grow and flourish in the days to come.